Good morning. In the previous lecture, we talked about different ways of accelerating your computation, and we briefly looked at how do we modify the current processor architectures. We also looked at how do you use field programmable gate array, and finally, we looked at graphics processing unit. And as we are going to talk about now tensor processing units. Before I talk about that, most of the acceleration of AI today is happening through graphics processing unit, and Google is basically this tensor processing unit is they are trying to create a competition, but GPU is still far ahead. So, let us talk about tensor processing unit. The key idea of tensor processing unit is a slightly different idea than what you have seen. The idea is called systolic array architecture. This is again from 1960s IBM days. Now, this got popularity, but because of the idea that how your neural network is. If you recall, we talked about different nodes and multiple layers, and some of them are connected differently, and then there are nodes, and finally, the prediction. This is where inputs are, and each of the edges you have Wi different way. This could be W0, W1, W2, and so on and so forth. What each of the node is basically computing is summation of Wi xi. Xi is 1 if that link exists, xi is 0 if that link does not exist, Wi is the weight on that edge. And during the machine learning process, the machine learning model basically learns that weight. So, the idea of tensor processing unit is effectively how do I compute this multiplication, because effectively if you are using neural network kind of machine learning model, it is nothing but multiplication. To be more precise, nothing but matrix multiplications. How do we do matrix multiplications faster? That is the bottom line. It just so happened AI, as I go along, when I talk about explainable AI, I will show you it is basically nothing but matrix manipulations. So, therefore, if we can do matrix multiplications faster, that is basically the acceleration. The difference between FPGA, remember FPGA can accelerate anything on everything, and if you want to accelerate your explainable AI, that is good too. Processor can run any program. If you want to run your multimedia program, that is fine, we will give you multimedia support, but this one can only do or effectively do matrix multiplication. The way the idea works, a systolic array, instead of spending and telling you an architecture course, if some input comes in here and if you compute something, that computation would be used by this cell as well as in this cell next time step. When this cell is done, it is going to provide this cell and this cell. When this cell is done, it is going to provide this cell and this cell. So, if you think about it like a waveform, if you throw a boulder in the river or pond, it creates that ripple. It is basically that ripple. In first cycle, these guys are computing. Second cycle, these two guys are computing. In the third cycle, these three guys are computing. In the fourth cycle, I do not remember 4, 5, 6, whatever, the next layer. That is how computation progresses, and final result goes through these layers. Now, you might think, how is this helping? Remember, in our original design, we are computing this Wi for this node, but whatever we computed, that is getting used by the weight multiplication for subsequent nodes. It is the same computation that is kind of percolating. So, whatever computation you did, and let us say you got a 5, from here that is the value that is getting or multiplied by certain weight, that is the value that is propagating. And if you try to recall how AI algorithm works, color is a feature and that has a more weight. So, computation kind of percolates, and if you can effectively do that faster, that is the systolic array architecture. Any of you have any confusion about this basic idea? Only thing I tried to highlight, how is it systolic array architecture, how is it different from other computations? This is not a generic, this is going to accelerate only if your computation or your program has computations like the neural network, only then it is powerful and useful. If you have a AI model or architecture that does not have a computation propagation, then it is not going to be helpful. It is not a general purpose acceleration like FPGA, it is not. So, this is very customized for accelerating neural network type of AI models. Any questions? Now, let me just zoom into little bit of the important aspects. So, this is basically this one I just zoomed in this box matrix multiplication, and I am trying to show what is happening. But in addition to matrix multiplication, there are few other interfaces, control, high speed data transfer, different types of buffer and interface and all that stuff. The reason these are needed or all this stuff, because remember, when you are operating on AI algorithms, it is used by somebody. If you think of a car, what is the input to this structure? In my class I am just saying, well, the input comes somewhere. Where does it come from? It comes from, in case of car, from sensors, the distance between the car, current speed, all of that contributes to the value. So, these are the values, analog values coming in, or sample discrete version of it. Those are the values, different types of sensor data coming in. That is why you need all kind of different types of interfaces and controller to do the data acquisition at speed, and then computation would be happening here. Then the result, whatever decision, slow down, what is the decision in the car? Either apply brake, so maintain the distance, or you just, if it is a upslope, increase the fuel injection to maintain the cruise controller speed, for example. Or if you are going down, then decrease the fuel injection rate so that it does not speed up beyond what you asked for in your cruise controller. So, those are the aspects, but I zoomed in only into the middle part. Any question on this? So, now I will show you the, I hope this animation will work. So, what you are going to do, every clock tick, which is a clock cycle or a time step in computation, the system clock data is passed to each processor from two different directions, then it is multiplied and the result is saved in a register. So, here are two sets of data, from one from this side, one from that side. Remember, we were trying to do Wi times Xi. So, this is a matrix, this is a weight data. So, you can visualize it, although this is not what I am illustrating. You can think of this matrix is this one and this matrix is this one. You have tons of edges, nodes, and millions of them to be precise, and they are coming from two sides. And as you will expect, so this set of values 342, 255 and all that thing, and 3. So, this 342 is basically this 342, 255 and all that, whatever, 253, 325. So, this data is basically this data, and this data is basically this data. Let me see if that is what it is, 323. Yeah, so this is 323, that is 323. Now, so I want you to understand one thing. So, this basically 342 is basically this 342, and here 323 is basically this 323. And the reason this way, if you recall matrix multiplication, the way it works, row and column. Now, as you, if you already have a good visualization power, you basically know these values would be pushed in from this side, which I will show in animation. These values would be pushed through this side. But normally you do not have to worry about it. I am showing you internal details. As an user, you simply put your AI algorithm and it would run on the TPU if you have a TPU. And these days you can buy TPU even in your USB drive. So, you can connect a USB drive, even if your computer did not come with the TPU, it would still work. Okay, so, let us see if the animation works. So, 3 and 3, and these are shifted by time step, these were intentionally done, and then 3 and 3 is supposed to come in. So, here I circle 3 and 3, those 3 and 3 is going to get into this P1 in the next cycle, that is the 3 and 3, and everybody else accordingly move in, and when this computation is done, you realize things would be moving on the right as well as down, and that is what is supposed to happen, that did happen. And then next set of values, so 4 was here and 2 was there, they are going to come down and they are going to compute, and then that computation again going to percolate, and this story will just keep continuing. until the 5 and 5 gets in and compute, and when there is, I forgot to tell you that the results of P1, P2, P3, whatever that result supposed to be, these numbers, if I go back, you will see these numbers are getting generated, added. Let me go back. So, initially it was started with 3 times 3 9, even before that it was 0. So 3 times 3, that is basically 9, and then once 4 and 2 comes in, that is going to be 4 times 2 8, that would be plus 8. So, similarly every computation, so you are basically going to have, so this is basically P0, P1, P2, P3. So, there are 9 elements, those are the 9 locations at the bottom. I am just trying to show what is happening in those values in a time step, and those values are keep on changing as values are progressing, and if you look and compute, you will see those are correct, and that is basically the final result you are trying to compute. So, what does this achieve you, this type of computation? So, in 2n plus 1 clock cycle, you will be able to compute it instead of n square, that is the speed up, theoretical speed up. Normally, if there are n element matrices, you would have need n square, but because of systolic array, 2n plus 1 is basically linear time computation of a multiplication, right. So far we basically talked about how do we accelerate different types of computation. Some of them are special purpose like GPU and TPU, some of them are generic like improving the CPU processor architecture or FPGA. Now, I am going to talk about how do we use this acceleration to speed up explainable AI, and there are a lot of works. I am going to zoom in into 1 or 2 of them or touch little bit of them. So, basically think about actually there are a lot of works. If you want to write paper, let me illustrate how you would write paper. You can do acceleration, here I am talking about 3, but actually you can do 4, and there are so many explainable AI algorithms, popular ones are 3 or 4. So, 4 times 4, there are 16 choices of paper, all of the combinations are not done yet as of today, right. So, there are 16 papers you can publish, but some of them has been done, most of them are on FPGA based. So, I am going to show only one of them. So, I am going to pick up hardware acceleration of the model distillation. If you remember in the explainable AI algorithm, I talked about decision tree is one of the simplest one. Model distillation is somewhere in the middle, then we have Shapley value analysis, then you have integrated gradients, there are so many algorithms. I am going to pick a middle one just to kind of illustrate, we have all these parallelism, why do not we just run this program as it is in parallel, why that is not good enough, I am going to illustrate that point. Or specific to explainable AI, what does parallelism mean, which fabric do we use, and if we use that fabric, what exactly do we do. So, I am just want to illustrate 1 or 2 of them, but before I go there I want to talk about acceleration and AI. AI acceleration is happening almost for 2 decades, and in fact GPU is inherently what it does is AI acceleration. Today all the GPUs that comes within your computer is basically tuned, super tuned for accelerating any AI algorithms you are running. So, that is why I intentionally decided not to talk about AI acceleration, then I will be talking more GPU, which we already did. So, what we talked in GPU is nothing but acceleration of AI algorithms. What we talked in TPU or systolic architecture is nothing but accelerating AI algorithms. Now, what is the difference of AI and explainable AI? The additional explainability, and the explainability, whether Shapley value analysis, whether model distillation, it has a lot of extra equation in addition to the equations you have or matrices or matrix operations you have for your AI model, and how do we make it faster. So, I am just trying to show you, this is one of the recent work, I am trying to show you what are the opportunities. So, in this particular one you basically have trust transformation. So, original computation that I wanted to do, that is not parallelism friendly. So, I want to transform and modify it. I will show you some example. Then some data the data I am dealing with, I want to decompose it, then parallel computation should be no brainer. Wherever you find a parallelism, you perform that computation, right. So, task transformation. So, basically as you realize in model distillation we also had the same thing. If you recall the model distillation we had model distillation we still had, remember we have the task we want to perform, and then on the top you have normal ML model, and then in the bottom you have the distillation model. You have the distillation model, and normal model, if you remember, they also look like this neural network and so on and so forth. These also look like neural network, right? It is a bunch of neural network. So, that is basically the distillation. So, we are basically talking about accelerating this one, but as you realize that is still a neural network layer, and that is still kind of a matrix multiplication story. So, in that context, so basically it boils down to still you have bunch of nodes, different weight, and you are computing the weights with that particular edge if that edge exists, and which boils down to again some weight matrix, and this particular is the corresponding node values matrix, and to compute whatever result you are trying to compute, that is the matrix multiplication you are computing. So, the in terms of so that is basically the matrix representation, and when you are transforming task representation, remember we are multiplying the, this is the input x, this is the input x. If you recall again what is the, where is the input? So, from the original layer this is the input, for subsequent layer whatever it produces that is basically the input for subsequent layer. So, input, and then you have the kernel k, and that produces the output y, right. So, kernel k is basically think of weight matrix. So, what we are trying to then compute, we are basically trying to compute this particular one through Fourier transform, and the way I want to explain this in layman terms without getting into the mathematics. So, somebody in the community already has shown if you have any computation in Fourier transform domain, if you are not from electrical you may or may not know, but in the Fourier transform domain if you have certain computation, then converting that to systolic array computation there is a natural mapping. So, somebody already established that. So, what was existing, if you had something in the Fourier transform domain to systolic array architecture mapping, that existed. So, what we had to do, whatever explainable AI model we have, the distillation model, if we can map it to Fourier transform, then we can make use of it. Now, as you can realize, this is, I want to go from nose to the eye, I actually gone to the head, then to the ear, then came to the eye. If any of you could find a natural mathematical way of mapping this, that would be much faster and better acceleration. So, that is an opportunity for you to do research. But nonetheless, this is the mathematical transformation, you are doing a convolution operation. So, this is the task transformation, our original computation was something, but we are transforming it. The reason we are transforming, as you know, somebody already showed how to go from Fourier transform domain to systolic array domain. We were just basically converting our activity into Fourier transform computation, and all these equations basically nothing but that is what it is doing. So, all I want to make sure you understand, this path existed, this is your destination, this is your source, your home, that path existed, there is a bus, train, whatever, all you have to go from this point to this point, that is all we did. Yes, please.
Sir, normal Fourier transform or DFT?
That is an interesting question. I do not know, I can check and tell. Is there a difference between normal Fourier transform and discrete Fourier transform?
Normal means I am talking about continuous Fourier transform.
Okay, so so this is going to be a discrete Fourier transform because we have discrete values of weights and edges. Yeah, this is, so this would be discrete Fourier transform. At least I learned something today. Okay, all right. So you could tell I don't have electrical engineering background. Now, any other questions on this basic idea of why are we doing task transformations, because we do not know how to go from here to here if I want to use the tensor processing unit. So, the next step, is data decomposition. So, again a lot of equations, I am not going to get into that. So, basically for the 2D discrete transformation, we are applying on this M and N signal, and you are trying to divide this data in such a manner so that it parallelism friendly, which is what we are going to do the next step. So, we are basically transforming, think of matrices, forget about this equation, we have bunch of matrices, transform all the rows of X input to obtain the intermediate results X prime, and then transform all the columns of resulting matrix X prime. So, basically this data transformation, so this is basically each of the row we are transforming in the X and in the resulting each of the columns. So, each row I and column j, that is what we are kind of obtaining, and what we are able to show through these equations, that these operation on these rows and columns are independent. So, therefore, you can perform them in parallel. If you have multiple core, multiple TPUs, you can perform in them parallel. So, it is not like okay, in a matrix multiplication, when you think of any matrix multiplication, not for this particular AI, when you think of you need to do multiplication of this row with this column, and there is some kind of implied understanding, I need to keep multiplying this element with this element, next one with next one, and so on and so forth, as if there is a sequentiality. Even if that is true, this one with this column and then this one with this particular column, all that can happen in parallel, and eventually when you add it up, that is fine, but those activities can happen parallel, and identifying those parallelism which compiler may not be able to identify. Then finally, when you do parallel computation, then basically all these different types of matrices or their different elements, you could technically, depending on how many cores you have, you could technically take each of the element for each of them for let us say multiplication or whatever you are doing, perform the computation, and then you kind of assemble. I colored them so that you kind of see where the computations are coming from, and then you are assemble them to get the from the remember we are trying to go to the Fourier transform domain. So, from the normal matrix multiplication to Fourier transform domain, once we have the data decomposition, we will be able to make use of different computing nodes and run them in parallel. So, if the basic idea is clear, you will be able to kind of do, and most of you or those of you are doing multi-threading, these ideas are kind of similar. Only thing is what we did, we took the explainable AI algorithm or model distillation problem and those matrix multiplications, and for that specific applications, what are the application level parallelism opportunities, I am just highlighting that. But you can just take your computation, give it to a standard parallelizing compiler, that compiler might be able to figure out all of these itself. You do not have to do any of these manually or explicitly. Now, how well does it work? I want to just kind of highlight how well does it work or who does work. Of course, remember this particular program is little biased towards TPU, because I picked up model distillation. If I pick up Shapley value analysis or somebody else, then GPU would so much better. So, in this example, as you can show, I am going to show different kind of data sets. So, this is basically GPU versus CPU is this one. So, GPU is faster, like for this kind of total performance per watt in same amount of energy, which one is giving better performance. So, GPU seems to be showing 2 times better. TPU is compared to CPU, TPU is showing 16 times better. So, 2 over 16, that is like this should be directly TPU over GPU is about 8.4 times better in terms of total performance per watt, and GM is geometric mean and weighted mean. But anyway, so point here is actual numbers are not important. So, incremental is basically excluding CPU power, and because we ran all of these experiments on our normal devices which has GPU, but remember CPU is also running there. So, to really get the real performance of GPU, ideally we should somehow subtract the contribution or whatever CPU is claiming, trying to just identify or isolate how much is exactly GPU taking, how much is TPU taking. That is the way we kind of try to do experiments, but whichever you want to do you can do, but no matter how you do, the numbers will kind of change. If the CPU contribution you get rid of, TPU would look significantly better, 32 times better, instead of kind of in this particular case 8.4 or 13.8 in this kind of example, weighted mean and geometric mean. So, in the bottom line in this particular analysis it shows, and as expected, TPU is going to do better than GPU and GPU is going to do better than CPU. But as I said, if you go for another explainable AI model, the chances are, and this experiment was done 2 or 3 years ago, in between GPU has gone through so much of transformation, the chances are GPU will do like exact opposite. So, TPU is doing 30 times better, now GPU will do 30 times better than TPU. That is possible if you do new experiments. Any questions?
Sir,
yes, please.
Just a big question, that
systolic array.
yeah, systolic array and this Fourier parallel processing using Fourier transform, which one is better, or are they just increments of each other?
So, the question is systolic array versus Fourier transform versus parallel computation, what is the relationship? Relationship is right here. So, relationship is we are trying to compute model distillation problem. So, starting problem is we have an explainable AI model that we want to map to TPU. In this context, let me put all the terms you said. TPU operates on systolic array architecture, that kind of very friendly natural representation of neural network. Now, somebody in the community already showed how to do Fourier transform to kind of systolic array mapping, which basically means TPU mapping. So, what we kind of did, took the model distillation and mapped it here. It is not anybody is better, it is basically a sequential relationship. We basically took our computation of matrix multiplication, mapped that to Fourier. Now, parallelism is orthogonal to any of these discussion. You can do this computation without considering the data partitioning and parallel computation, or you can do this. So, the parallel computation help, can I use 2 TPU, 4 TPU, 6 TPU, 32 TPU, can I make use of that? If you are using 1 TPU, parallelism does not even come into the story. If you are using 2, 4, 8, 32 TPUs, then it is basically saying you do not have to treat it as that matrix 1 and matrix 2, you can deal with column 1 of matrix 1, sorry, row 1 of matrix 1 and column 1 of matrix 2, row 2 of matrix 1, column 2 of matrix 2. So, then those can go to TPU and systolic array, and that can happen in parallel. So, parallelism is orthogonal to this idea. Any other questions? So, in terms of scalability, so scalability basically means the problem size of the matrices. If you keep increasing think of size of the neural network, if you keep increasing, who scales in what way, and as expected when the problem size, remember the weight matrix multiplied by the AI matrix. So, that is the weight matrix and that is the other matrix WIXI. So, the CPU is going to very quickly going to take a lot more time. So, this is the time axis, this is the how complex those matrices are, how big that neural network is, it is going to be extremely slow, and that is expected. Now, in this particular example, remember this was done 3 years ago, this particular example GPU is kind of not as bad as CPU, not as good as TPU in terms of problem scaling and the time it takes to compute. And again remember, two things are in advantage to TPU, it is 3 years ago, GPU was not that level as today, and second thing was this particular problem model distillation is more friendly for systolic array computation. So, this was a bias towards TPU. So, basically to kind of, this is a conclusion for today's lecture. So, there are lot of widely used hardware accelerators methods. So, field programmable gate array, graphics processing and tensor processing, and explainable AI algorithms are complex, and unless we utilize kind of acceleration, they are not suitable for many real world systems. So, basically in the next lecture we are going to talk about malicious software malware and discuss how explainable AI can be used for malware detection. So, we have a lot of time. Anybody want to discuss questions, go back to any of the material or make the connection, I will be happy to talk. Do you have any questions? Go ahead.
Particularly Fourier transform maneuver was do. So suppose we are doing polynomial multiplications. Suppose you are doing polynomial multiplications. Polynomial multiplications is suppose you want to multiply two polynomial of order n size. It is actually order of n square complexity. But if you convert into Fourier domain, then converting to Fourier domain, one polynomial will take n log n time, another polynomial n log n. So it can be done in n log n time, and multiplication in Fourier domain is actually additions. So now instead of multiplying, you are doing in actually addition domain. So addition of two polynomial, it can be done in order n time. So effectively, order of n square algorithm is getting converted into order of n log n algorithm. So can here also it is doing similar kind of thing. So multiplication is order of n cube or matrix multiplications.
Right. So, the question is interesting. Question is, if we map a problem, matrix multiplication problem to polynomial manipulation problem, so then you could potentially convert into multiplication to addition or order of n square to order of kind of n log n problem. And if I do tensor processing or systolic array, that is kind of order n problem. So, then question is, are they conflicting idea or compatible? They are actually compatible, because going to Fourier transform domain or that computation or the way systolic operate, so it is actually same, the way the computation or the flow of data is actually systolic array computation. That is why when I said the mapping existed, that Fourier transform you can naturally map to systolic array. So, in other words, if you go through Fourier transform domain, instead of order 2n plus 1, it is going to be order 2 n log n plus 1. So, if you go directly, or if somebody can find a direct way of going, it is order n. If you go via Fourier transform, it is going to be order n log n, because mapping of n elements or n square element, it takes n log n. So, it is basically order n log n. It is slightly more complex than if somebody can figure out directly going to systolic array mapping for the explainable AI.
Can you think of a serial algorithm? So, because matrix multiplication complexity, serial complexity is actually n to the power 2 to the power 6 1, I think so. It's not n cube, but n to the power 2.
Little
if you do Fourier transform, then it can be done in lower, but no one have reported kind of thing. It may not be directly possible in terms of, but exactly may not be possible maybe.
Okay.
Otherwise, theoretical result may change.
Yes, absolutely. There was another question here, somebody. Yeah, go ahead, please.
Sir, I am little bit confused in data decomposition thing, like how it is connecting with the task transformation and parallel computing.
Okay. The question is the task transformation, and that is why there is this first overview diagram. So, data decomposition, task transformation is basically you are taking an explainable AI algorithm and converting into matrix multiplication algorithm, that is it. So, if you are standing at this point, you actually do not know whether it came from AI algorithm somewhere else. All you see here bunch of matrices and you are doing multiplication of them, that is what you call it task transformation. If you want to call it something else, it is fine, but basically you are taking some concepts of neural network and you are talking about matrices. In fact, in the AI domain, it is all about linear algebra, manipulation of matrices. In fact, now that we have time, I can talk about little bit about quantum machine learning. Even in quantum domain, it is all about manipulation of matrices. It is just that the elements of those matrices are different. Any other questions?
I have one question. So,
Sure.
and I have seen many work that try to map this
a trained model into FPGA, right? So it can be for explainable AI, for any other ML model. But usually the training process is never been done on FPGA, right? So I mean, I have not seen much work that try to map the training process is also an algorithm, right? So
Right. So, interesting question. The question is, we talked about different acceleration algorithm and we talked about all of this stuff, and what I did not talk about or kind of implicitly assumed that all of these acceleration I talked about, it's about the trained model, whichever will do the final computation. So, if you recall, in the AI model there is the training part. So, there is this training component and then there is this prediction or final deployment, whichever you want to talk about, where you basically make basically prediction for classification or finding a value for regression or whatever type problem it is. All the acceleration I talked about, I forgot to mention, it's all about this one. You accelerate this one, because nobody cares, or mostly nobody cares about how much time, how much effort, how long you take in the training time, and training today is de facto in GPU. This is de facto, but for this deployment or prediction we talked about various choices. We talked about FPGA, we talked about GPU, we talked about TPU and all that stuff, and it is quite possible eventually these also will be default. Oh sorry, I mean these days many people use FPGA actually more than GPU, and the reason is GPU is trying to do certain computation, but you still have all these data movement and all that stuff, but in FPGA you just program whatever the model is once and that is the thing going to keep on running. It is like then you kind of formed a hardware which is supposed to run faster than GPU, where things are moving around with the inputs. So, most of the people are kind of try to use FPGA here, and here of course the de facto is GPU during training time. This is the same analogy of compiler in embedded systems. You can take as long as you want to compile, but when you compile the code, that need to be tiny, small, fast, quick, that is this idea.